atmospheres of planets in other solar systems, so figuring out what the atmospheres are made of, and maybe how the planets formed and what conditions might be like on their surface. So if you've got any questions at any time, I don't know, do we have guidelines? As far as I'm concerned, feel free to ask any questions you might have, and we'll do the choo-choo and we'll have some trivia questions. All right, so small planets and small stars. So this sort of schematic diagram, I like toy schematic diagrams. This cartoon up over my head shows a couple of different astronomical objects to scale. So over there on the right-hand side, a big thing that doesn't even fit in the whole screen is the sun. Our sun is sort of like a middle-sized star. There are some stars that are a lot bigger than the sun, and they really wouldn't fit on this plot. But also there are some stars that are much smaller than the sun. And so I put a couple of these on here. So the sun is what we call a G star, or specifically astronomers would call it a G2 star. But there are other types of stars with other random letters that don't mean anything because they were assigned 100 years ago when astronomers didn't know what they were doing. Now we think that we do, and we call these smaller stars M stars. So that orange one there is what we call an M0. It's about half the size of the sun. And that little red thing we'd call something like an M7 star, so only maybe 10 or 15% the size of the sun. And these colors are really different. The sun we think of as sort of a white-yellow, very hot star. And these M stars are not only smaller than the sun, they're also a lot cooler. So they might be only half the temperature of the sun, so still hot enough to vaporize any of us, but a lot cooler than the sun is. So their colors are different. And then I've also put up there a couple of planets that may or may not be familiar to you all. And you can see that actually some of these small M stars, these small red stars, are actually only a little bit bigger than gas giant planets. And so they're fundamentally different in lots of ways. A star is undergoing nuclear fusion in its core that generates energy and it'll shine for a long time. Jupiter is very cold and doesn't have as much material, and there's no fusion. But nonetheless, they're about the same size. Even though the one is much heavier and brighter than the other. And then there are some even smaller planets up there too, Neptune and the Earth, which you can barely see if you're sitting in the back. So for the purposes of this talk, when I'm talking about small stars, what I'm talking about is specifically these M stars that are sort of half the size of the sun or less. When I talk about small planets, these days we've found and we know about lots of gas giant planets, things the size of Jupiter. And someone was actually asking me before the talk started, you're not going to talk about those Jupiter-sized planets again, are you? So don't worry, I'm not going to tell you much about them anymore. And even these days, even Neptune, in another solar system, we wouldn't necessarily think of it as a small planet. So we're really talking about things smaller than Neptune in this talk, around small stars. So they asked me to put in trivia questions. So here's your first one. What's a common technique that astronomers use to discover planets around other stars?
Stars? Spectroscopy.
So I heard something I didn't understand there. That's right. Spectroscopic techniques is one, definitely, and I heard another one over here somewhere.
Transiting?
Transiting is another one. That's right. Any other?
Where was the spectroscopic?
All right, so there's a couple common ways astronomers discover these planets. One of them is the spectroscopic technique that I'll talk about in a moment, which uses the Doppler shifts of the light coming from stars. Another is the transit method, which look for stars that get a little bit dimmer and then a little bit brighter again. And then another method, which I won't talk about too much, but which you do a lot of work with at University of Arizona, is taking direct images of planets and actually spatially separating them in the sky from their star. I'm just going to briefly go through these first two techniques because these have been some of the most productive we've used in discovering new planets. So this first one, the Doppler shift, is, you remember what the Doppler shift is? You remember it's what those cowboys are always talking about when they say, there's nothing I like more than what is this? The lonesome wail of the train whistle as the frequency of the wave changes due to the Doppler shift. You know, this is what those cowboys are, what we'll be saying as soon as one of these trains comes along. And so the Doppler shift, if you cast your mind way back to when you or your kids, depending, were studying physics in school, the Doppler shift is what happens when you're emitting waves like sound waves and you've got an object that's moving through space. So for example, a locomotive, when it's sounding its train whistle, If it's moving toward you, you hear a slightly higher pitched sound. And if it's moving away from you, you hear a slightly lower pitched sound. That's just called the Doppler effect. And so this happens with sound waves, and we'll be able to hear it as these trains go by. But it turns out that light, like the light that we see with our eyes, also acts like a wave. And so the Doppler effect can also affect light waves as well, if say, a star is moving back and forth. So one of the ways we look for and find planets is if you've got a massive planet orbiting a star, the planet's gravity, the force of gravity between the planet and the star tugs on the star just a little bit. So the planet here is very dark. From Earth, we can't see the planet at all, but we can see the star because stars are really bright. And we can watch as the spectrum of the light from the star is Doppler shifted back and forth, just like there was a train that was going away from you and toward you, away from you and toward you. And you'd hear a sort of Doppler shift in the sound, but we can see that in the light waves. So using this Doppler effect, we can estimate, we can find that there's a planet orbiting that star. And we can also use this to figure out the mass of the planet, how much does the planet weigh. That's all it would tell us about the system. So another way we do this, we find planets through the transit method. And in this case, you look at a star and measure how bright it is over time. And as a planet crosses in front of the star gets a little bit dimmer, and then once the planet is out of the way, the star gets a little bit brighter again. And so if you look at lots and lots of stars, and you see lots and lots of dips in the light that occur very regularly, then you can infer that maybe there's a planet there. You can do you can follow it up and look at it in other ways to confirm that, yes, there is a planet. So we found lots of planets using both of these techniques, the Doppler shift technique and these little dips in light, these transit searches. So the Doppler shift effect tells you something about the mass of the planet. The transit tells you something about how big the planet is. So between how big it is and how massive it is, how much the planet weighs, you can figure out something about the density of the planet and maybe what it might be made of. So maybe a very high density planet would be made mostly of rock. Maybe a low density planet would be made mostly of gas, like a gas giant like Jupiter or Saturn. So from these techniques, we've discovered lots and lots of planets, and we can study something about what they must be made of. Choo-choo. Look at that Doppler shift. I'm sure you get it when it's only 10 miles an hour. Okay, great. So using these techniques, the Doppler shift and the transit technique, we've discovered thousands of planets around other stars. So when I and many of you were going through elementary school, we knew there were just the planets in our own solar system. And that was it. We didn't know about anything else, and people speculated. But now, just in the last 20 years, which is not so short, but it's not so long, we've really had a revolution in our understanding of our place in the universe. And so this plot here, which is blank at the moment, shows on the horizontal axis here the length of a planet's year. So how long does it take a planet to go once around its host star? And on the vertical axis, the y-axis, how big is the planet relative to Jupiter? And so we can put some solar system planets up here. And so up there in the upper right, we've got Jupiter because it's very far from the sun. It takes a long time to go around. And it's very big. Down there in the bottom right, we've got all of the inner planets in our solar system: Mercury, Mars, Venus, Earth. The other planets in the solar system are so far out they wouldn't even fit on this graph. You might be wondering, well, why has he left so much empty space? But it's because the exoplanets we've discovered from these techniques totally fill this parameter space. And we're not very sensitive yet to planets like those in our own solar system, but we've discovered without a doubt is that many solar systems are utterly unlike our own solar system, completely different. We've got up in the upper left here, you've got lots of big planets in very short period orbits, very close to their star. These are these hot Jupiters someone was asking me about earlier. Down there in the lower left, we've got a large cloud of planets, many of which are bigger than the Earth, but smaller than Neptune, and but they're still all very, very close to their star. Being close is something of a selection effect. It's tough to find things that are far from the star. But the point remains that almost any of these dots here, with a couple exceptions, are not like any of the planets in our own solar system. So these other systems around other stars are totally different, unlike and very alien to us. And this came as a big surprise to astronomers. We thought we had it all figured out 20 years ago and that everything would look like the solar system, but that's definitely not the case. So it's exciting because it creates a lot of opportunities for us to discover these things. So I'm going to give you 3 key points to take home. Point 1 is just the fact that using Doppler shifts, like we hear with train whistles, and looking at little dips of light as things pass in front of stars, we've discovered thousands of planets, and these are totally unlike anything that we see in our solar system. So very, very cool stuff. So second part, trivia question then. So what spacecraft has discovered more planets than any other?
Kepler. USS Enterprise.
Nice try, Fred.
So I heard the right answer there, which was the Kepler mission. The Starship
You just stick
Enterprise.
your hand up when I said Kepler.
So the Starship Enterprise, it turned out, had it wrong. The Starship Enterprise had to fly around from one star to the next, and then when they get to the solar system, they find, oh well, we discovered 2 more planets in this solar system. But it turns out they weren't very smart in the Federation. We can have space telescopes here on Earth and orbiting the Earth in space, and we can discover thousands of these planets without ever even leaving our home. So the Kepler spacecraft, there's sort of some basic data and statistics shown up here for the Kepler spacecraft. This is a moderately smallish space telescope built by NASA, and it's been operating now for about 6 years up in space, orbiting around the sun. And it's observed many hundreds of thousands of stars. And it's the single most productive tool that we humans have ever had for finding new planets around other stars. And so as you can see here, it's found 4,000 or 5,000 candidate planets, most of which are probably real planets, over 1,000 things that are already definitely confirmed, absolutely these are planets. It's downlinked many terabytes of data, which is publicly available. Feel free to go and play around with it after this if you want. Kepler is a great planet-finding machine, and it's one of the things that's really revolutionized our understanding of That one snuck up on me. All right. So, Kepler. So Kepler has discovered, as I said, thousands of solar planets, thousands of solar systems around thousands of alien stars, some of which are hundreds or thousands of light years away from our sun. And so this movie up here, which I find quite mesmerizing, is just a subset of some of those planetary systems. So up in the upper left, this is actually our solar system. Those are the 4 planets, the 4 inner planets, Mercury, Venus, Earth, and Mars. And all these others is just some of the thousands of planets that Kepler has discovered just in the last couple of years alone. And so now we zoom in on here and you're all getting very sleepy. You like finding planets. Good. And so you can see that many of these planets, I should say that the dots here are not to scale to the orbit. We don't actually have planets crashing into each other or going through each other. That's just so you can see the planets. Space is really big, otherwise you wouldn't see the planets at all. But the point of this is that there are tons of planets, and many of these solar systems don't look, again, to emphasize the point, don't look anything like our own solar system. You have these planets that are on extremely short orbits, they're very tightly packed with lots of planets very close to each other. I mean, what's going on? How did these things form? We're still learning and trying to understand that. We really don't have ironclad answers yet. So Kepler, yeah. That's right. Yeah, so the question was, isn't there a bias here? Because Kepler only observed for a few years, so obviously you wouldn't see planets on really long periods. You wouldn't expect to find anything like Jupiter or Saturn, which takes many years to go around. And of course that's right. So Kepler, like any observing technique, has its own set of biases, and one has to account for that to figure out what types of planets are truly more common than others.
Follow-up question. So K2 allow that to trace?
I'll mention that briefly. The question was, I'll get it. Ask me again if I don't. Yes?
Can you determine statistically what the distribution might be of
such planets?
The question was, can we use that crazy movie I just showed you to figure out what is the intrinsic distribution of planets around stars, correcting for these detection biases? And yes, absolutely. So I'll talk about that in a moment.
Okay.
So, showed you all of these solar systems. So then, what's the most, another trivia question, opportunity to win a poster. What's the most common size of planet? This is something that Kepler has measured that we really only had a vague, rough idea of before this. So it could be gas giants, things like Jupiter and Saturn. Could be smaller, what we call ice giants, like Uranus and Neptune. Maybe it's small rocky planets, like Earth and Venus. So maybe it's something else. Maybe it's asteroids. But we don't know about exoasteroids, so that's not a valid answer. Only scientifically testable answers will be accepted. Any takers? What's the most common size of planet around other stars?
Gas giants?
Okay, I heard gas giants. Since we're not handing out the poster yet, I guess that you all know you have another chance now.
You're gonna say ice giants?
Okay, I heard ice giants.
Earth size.
Earth size, there we go. Process of elimination. Yes, so it turns out that, believe it or not, planets, should be showing up there, planets the size of the Earth are actually the most common types of planets. So even though big planets like Jupiter or Uranus are much easier to find, these smaller Earth-sized planets, even though they're tougher to find, actually turn out to be intrinsically the most common types of planets that we're able to detect. So this is a histogram plot here, and so on the horizontal axis, this black curve is showing how frequent are different sizes of planets. So Earth-sized planets are over here at the left, Neptune-sized in the middle, and Jupiter-sized ones over here on the right. And you can really see this is a dramatic effect. So 10 years ago, all we were finding were hot Jupiters, things the size of Jupiter, because they're so easy to find. They tug their star a lot, the big Doppler effect, a big dip of light. But Kepler is sensitive enough that it showed us that we actually, and so this is now corrected for all these detection biases. So really intrinsically around other stars, Earth-sized planets and somewhat bigger are actually the most common by far types of planets. And right around the size of Neptune, maybe a little bit smaller, there's this sharp cliff, and the occurrence of planets just drops off. So something in the process of planet formation really disfavors anything bigger than about 3 times the size of the Earth. And so even Neptune is kind of an oddball in this sense. Even it is something like 4 times the size of the Earth, and so those are still not very common. So this is revolutionary. Just a few years ago, no one knew anything about the occurrence rate of Earth-sized planets. And now I should point out, we're not talking yet about planets with the temperature of Earth, planets that you could go and live on. We're just talking about size. So many of these things found by Kepler are in very short periods, very close to their star, very hot. Wouldn't want to go there. Like molten rock covering the surface of many of these planets. Uncomfortable places. But still, the planet size is roughly the size of the Earth. And these are the most common types of planets. So not only was Kepler able to measure this, but it can also measure how common are different types of planets close to or far away from their star. And so this plot is going out a little bit on a limb here, but this horizontal axis is still the orbital period of the planet, so how long is its year. And this vertical axis, again, is the size of the planet. And the color shading now is how common are those types of planets around other stars. And so the dark region up here, near these big planets that are close to their star, hot Jupiters, turns out are very rare. They occur around something like 1% or less of all stars. Whereas planets down here, much smaller planets, on much longer period orbits, occur around something like 10 or more % of these types of planets. And so maybe this suggests that planets with the size and maybe even temperature of the Earth, maybe these are actually pretty common. And so there's still a lot of debate about exactly what that number is. How common are planets with the size and temperature of the Earth? Because that's something we'd really like to know to put our own planet, our own home, in context in the universe. But there's no question that in general, there's this trend toward more planets that are small and more planets that are cool. So that's the second take-home point here, that most of these planets that we found And the most common types of planets are these small planets, 2 times the size of the Earth or smaller. Question?
So, a quick question about the biases that Kepler might have. Because it's been observing for a short period of time, you would expect to see more of these transit events with the smaller planets, correct?
You'd expect to see more transits for a shorter planet year.
Okay. Does that necessarily correlate with planet size?
Sorry?
Does that correlate with planet size or planet mass?
It correlates with planet size in as much as the smaller things are more frequent, and they're more frequent around on longer orbital periods.
So Kepler would see more of those objects than they would see larger objects or more massive objects.
That's right, so this study here corrects for the fact that we're more likely to see transits from big things, and we're more likely to detect transits that occur many, many times.
So that's my question, right? If you were to look at our solar system from afar, Jupiter is obviously a large massive planet, but we have other gas giants that are contributing to that kind of stroboscopic shift that tries to indicate that there are those planets there. So how do you take that into account?
So that's intricate enough. We should talk about it after the talk. But come up and ask me. So we find these planets from Doppler shifts, and especially from these transits, from these dips in light, and we found thousands of these. And it's revealed for the first time that these small planets are the most common types of planets in the galaxy. So things we never knew before. So third and final part. So another trivia question for you. What's the most common type of star? So again, up here, I gave you a couple examples of different types of star. Up at the top, we've got a red giant that's so big. You know, that red giant is as big as this building. We've got sun-like stars. We've got our red dwarfs, our M stars. We've got white dwarfs. We've got neutron stars. There are other types too. But what's the most common type of star?
White dwarf.
I heard a white dwarf. I heard a white dwarf. I heard a red dwarf. Red dwarf is right. Red dwarf gets the prize. Because the name of the talk is small stars. So. I said to be the first to buzz in on that one. Yes, so it turns out that, was that a question?
Just a real quick question. These solar systems that are way, way out there, how do you know, despite the wobble of the star itself, that there's more than one planet? How do you know it's just not one large planet that's causing the wobble or multiple planets?
The question was, how do you know that a system around another star has multiple planets? How do you know it's not just all being caused by one big planet? And the answer to that is if you're using transits, depending on the year of the planet, how long it takes it to go around the star, you'll see the transit spaced by that amount of time. So if there's a big planet that goes around its star every 50 days, you'll see one transit every 50 days. If there's a smaller planet that's going around every 10 days, then you'll see the big transits every 50 days, and you'll see little transit every 10 days.
So then when you initially are looking at something, you look at just the wobble, then look at the transit, or is it any sort of step that you do?
So it's gone both ways. There have been some systems we found by the Doppler wobble that we then discovered to transit, and there have also been many that we discover with Kepler to transit, and then we go and measure the Doppler wobble. So it goes both ways. So most common type of star is these small red M stars. And by far, so in school, maybe your elementary school teacher told you the sun is an average star. In some sense, that's true. But in terms of the what's the typical type of star in the solar neighborhood near the sun, this video is showing all of the stars that are near to the sun. And if you look at all these things, you actually see the sun is sort of yellow, but most of these little points of light are actually much redder than the sun. Actually, most of the stars near the sun, near our solar system, are not stars like the sun. They're actually these little red dwarfs. So the most common type of star is a red dwarf. And so this histogram here shows that. So because we're astronomers, we put a lot of things backwards. So here, bigger stars are on the left. It's true. You laugh, but it's true. Bigger stars on the left, smaller stars on the right, because we're all kind of perverse that way. And what you see here is that all these red shaded things are M dwarfs, and by far these outnumber all of the other stars. And these are all the stars within about 20 or 30 light years of the sun. So Most of the stars are not stars like the sun. The sun is way out here. This is one solar mass. This is the mass of the sun. But most of these things are half the size, the mass of the sun, or smaller. So the typical star is a small, puny, cool, low-mass red dwarf. Boring. But it's also really cool. Because, that's right. So what we found is not only are these small M dwarfs the most common type of star, but UA's very own Gijs Mulders, who's here in the audience, did this great work, which actually showed that so this is showing how frequently do small planets occur as a function of how far they are from the star. And this yellow curve on the bottom is for stars like the sun, and this red curve up on top is for small M dwarfs. And what Gijs found is that these small planets occur 2 to 3 times more often around M dwarfs than they do around big, hot, sun-like stars. So what does that mean? Let's think about that. So that means most planets are small, 2 times the size of the Earth or less. Most stars are small, half the size of the sun or less. And these small stars intrinsically are more likely to host smaller planets orbiting around them. And so what this means is that these small planets orbiting small stars, these are the most common types of solar systems in the galaxy. So we thought we live on the Earth, when we live in the solar system, everything must be like the Earth and the solar system. But it's not true. We are really atypical, if only because our planet orbits a hot, yellow star like the sun. Most planets don't. Question?
So, but what happens if it's a big star and it's just a small planet and it doesn't affect that wobble that you're talking about?
That's right. So the question is, what happens if you're around a really big star, and we might not be able to detect the planets around it because the wobble would be smaller, or the star would be bigger, so the transit would be much shallower. And that's true. And we don't know too much about. So if I go back a little bit, we don't know too much about planets around stars more than about 1.5 times the mass of the sun. We don't know much about planets there. But in Gijs's study, I simplified this plot, but he went out to about, he covered most of the range that's plotted here. And as you went to higher and higher, to bigger and bigger stars, after correcting for the fact that we're not sensitive to those planets, they still have fewer planets. And also those stars are so much less common than M dwarfs that even if they all had 10 planets around them that we couldn't see, probably most of the solar systems would still be around them, small red stars. So these small planets orbiting small stars, these are the typical solar systems. And we've only discovered this in the last year or 2. So it's really remarkable to know about this. And so this is exciting for lots of reasons, because planets around small stars is that when the star is smaller, the reverse of your comment just now, the star is smaller, so it's easier to detect the wobble, so it's easier to detect the mass of a planet around an M dwarf. The smallest star is smaller, so the transit is deeper, so it's easier to measure the size of the planet around the red star. So actually there's a big advantage, and it turns out for the same reason, it's also easier often to study the atmospheres of the planets orbiting the small red stars. And so this means there's this in the field of solar planets and other solar systems. It's in many ways much easier to study these sort of planets.
So does this have significance for limiting the theories of how both the planets and the stars have formed, and maybe the interaction for them?
The question was, does this all have implications for theories about how planets form? And the answer is yes, definitely. There are implications. I think precisely what they are, we're still working out. It might be that these small planets or these small stars, something about them is intrinsically more efficient at forming planets, or it could be that that they all form planets equally, but something happens to the planets around the big stars. They quickly spiral in and are engulfed by their star. They they come close to hitting another planet, and gravity shoots them out of the solar system, and we never see them again. So there's still lots of active work. So in the future, what we've got is a timeline. Whoa. Sorry, I don't know what happened there. So we've got today. Let me get this back. All right. So maybe my new laptop is actually in the mail. So this is a sign that it's time to ditch this old one. So we were about to finish up anyway. So what I'll just say is, so right now the Kepler satellite, the spacecraft, is still up there, still finding new planets. It's actually it's been reborn as a different mission, a slightly different mission called K2 instead of Kepler. And this is it's appropriate that this talk is on Veterans Day, because actually Kepler is a real space veteran. It actually had, you can think of it as it had these four devices that control where it can point. Think of it like 2 arms and 2 legs. It had 4 of these, and it's lost 2 of them in the space wars. They just broke down. So Kepler now just has, it's like I don't know. Kepler's a veteran. It's now K2, but it's still doing amazing science and finding new planets. We're already finding lots of planets using Kepler and K2, whose atmospheres we can study with the Hubble Space Telescope. And in just a couple years, another mission. Great. In just a couple of years, NASA's launching another mission called TESS, the Transiting Exoplanet Survey Satellite. And whereas, I didn't talk about this, but whereas Kepler and now K2 just look at a pretty narrow patch of sky at one time. It can't see the whole sky at once. TESS will actually look at the entire sky, and every star in the sky, and it'll find all of the transiting planets around the nearest stars, around the brightest stars, around the systems that are most amenable to follow-up, to measure their mass, measure their size, study what their atmosphere is made of, study whether there might be life there someday. And so TESS will just launch in a couple of years. And then soon, hot on the heels after TESS, will be the James Webb Space Telescope. You can think of this as sort of the big brother successor to, or that being the younger brother, of the Hubble Space Telescope, which has been doing so much amazing work up in Earth orbit. And James Webb is, among other things, really going to be an amazing planet characterizing machine. It's going to be the superlative facility for characterizing the atmospheres of planets orbiting other stars. We've got nothing else that's going to compare to it in any way. And so this is actually timely, because just today, if you're an aficionado of astronomy news, then maybe you read about this planet that was just announced today by astronomers at MIT and Harvard. So Zach Berta Thompson, who is a really good guy, led this study, and he discovered, you can go home and read about this, discovered the nearest transiting planet to our solar system. And so this planet, this is just an artist's drawing of the planet near a small M-dwarf. But it's a small Earth-sized planet orbiting an M-dwarf that's only 20 or 30 light years away. And it's the closest, it's by far the closest small planet we know about, and the lowest temperature. It's not, so it's roughly Earth-sized, it's not low enough temperature that there could be liquid water on it. It still wouldn't be pleasant to visit. But it's really exciting because it's so close, because we found it now, before all these other space telescopes even get off the ground. So we're going to have really all sorts of opportunities to study this, and we have every reason to think that we'll find many more planets like this, hopefully some even cooler and even more like the Earth. So with that, we find lots of planets, and we didn't do this just a couple of years ago. We find small planets down to the size of the Earth, occasionally even smaller, and in very long periods, very cool temperatures, and they orbit small stars. These are the typical planets in the galaxy, and it's great because it gives us the best chance possible to study them and learn everything we can about them. So, thanks for coming. Happy to take any more questions. We only got 2 choo-choos. That seems low.
I mean, you can hop in.
Question.
So is there a limit to how far away these stars can be with our current techniques that we can detect planets around them?
So the question was, is there a limit to how far away these stars can be for us to detect planets? And the answer is definitely yes. As a star goes further and farther away, it